Okay, this is what we came up last time. So it's quite unsorted and not very structured. So I came up with basically similar ideas, but a little bit more structured, and I also added some information that is more specific to the booster K1. So in the beginning, we have some data that you can get from the SDK, and we would write it to the Blackboard. Blackboard is just a data structure that just can hold data. So the analogy would be a blackboard in a school, and all those pieces of code or modules that write to the blackboard could be considered like the students that need to come up to the blackboard and solve the task and write the results on the blackboard. So this is basically what those boxes are. Yeah, so we write the image, we write all the data we get from the sensors, meaning the positions of the motors. And of course, also if we record audio, the audio should also be saved somewhere, so future modules can access this. Then we also discussed in code a little bit. We have a module that receives messages from the game controller. In the end, later on, it should go into another module that actually decides the game state, because in some parts what the state of the game is doesn't not solely depend on the game controller, but also if there was a whistle detected, for example, which signals the actual start of the gameplay. In previous years, we also had different rules where we needed to detect the referee and different referee poses. And that would signal the start of the walking into the field phase. Yeah. So, and maybe in the future we will have this again. So, and all of this together gives us the game state. So basically, we need to do all of this right to even know what to do on the field. Yeah. When we actually are in play, we need to detect visually all the different things on the field. So obviously this would be the ball and our teammates and the opponent robots, and then we can decide of what we want to detect. Do we want to detect the lines? Do we want to detect the intersections? This would depend on how we want to do our self-localization. On the booster, what kind of works very well with the heights they have is just detect the intersections, and from that do a relatively simple triangulation that already give you the position on the field. When we detect this in the image, all of this, we need to also calculate where it would, where those things would be relative to the robot on the field, and we want to not just use the detection but also model this. So we, if we detected the ball a few frames before, and we don't see the ball anymore, we could have a model that like, oh, the ball is still likely in that area, and the same thing for everything else. Of course, we would need to account for our own motion in those models, but we absolutely need some sort of modeling here to account for missing detections. Just by the nature of the game, if you have at least 6 robots and a referee running around on the field, you won't see everything in every image. when you have either the lines or the intersections detected and projected on the field, we can then use some sort of self-localization, still pending a decision on how we want to do this. Yeah. And if we know our position on the field and everyone else's position on the field, we can sort of write a strategy on what the robot would do. So the simplest thing would just be look around for the ball until you see the ball. If you see the ball, go to the ball. When you're near the ball, turn around the ball towards the opponent goal and then walk straight towards the ball or kick it. So this would be a very, very simple strategy that would at least win against an empty field. So if other opponent robots are taken out or just broken in the first place, we would win with this kind of strategy. And our goal should first be to achieve this win against an empty field. Yeah. So last time I said that we need to listen to the game controller to at least have a legal gameplay, but also the rules specify that we need to send some data back. Otherwise, the game controller would think our robot is dead and doesn't listen, and therefore we would be punished by being disqualified for the game. So we need to send some data. This is basically just the position where we think we are on the field and where we think the ball is relative to us. What values we send doesn't matter. It could send random values. We wouldn't be punished for this. The important thing is that we send something. And if we decide on doing some team communication, we would also need to send this in the end. And usually what you send in team com is you send also your position and where you think the ball is relative to you. Yeah, and in the end, after we did all the processing of all the information, we need to give our RL policy some input of what needs to be the movement. And for a walking policy, for example, this would just be the heading in which the robot should walk, the walking speed, and that's basically it. And then the robot would walk. Yeah, that's all for like a really minimal implementation. So what's still missing here is we don't have any logging here. Usually what you want to log is you want to write the data on the blackboard for this timestamp into a file. Yeah, so we would have another module in the end that would write everything on the blackboard, or everything we want from the blackboard to a file. And this is also would be append only log file. Yeah. Also, what I didn't consider at all here so far is any kind of debugging functionality. So with the NAOS, we had a tool called Robot Control that could connect to the robot, and then you could live visualize the data from the blackboard. So if we have this built in Rust, then we can also have a look at how to do this. Yeah. Also, I didn't consider that we might want to run the whole code in like a Muchoco-based simulation. So this is what other teams are doing, for example, to improve and debug their strategy. To me, those kind of things can be done later and are an add-on. So what I considered here is everything that I think we need for a minimal gameplay, and that what would win against an empty field. And yeah, as soon as we achieve this, we can go a little bit more complicated. But yeah, that's it for the whole structure. and then we would continue with implementing the game controller receiver and building this module architecture with the Blackboard in Rust. And we do this in the next video.